Hi, let's discuss Fenwick trees. Fenwick trees are basically binary index tree. We use them to find range sum queries. So here in Fenwick trees, what we do have leverage against the prefix sum is that we can find range sum from prefix sum too. However, we cannot have a efficient update methodology in prefix sum. If we want to update prefix sum, any index in the prefix sum, suppose from here it is 1 3 6 and 10 and 15 and 21 and 28 and 36. Suppose we want to update this I to 6. We have to update all these values to efficiently find range queries. So for updating in prefix sum, we have a first time complexity of O of n. However, to alleviate this, we need something better, and something better in terms of time complexity. So we have Fenwick trees here. Fenwick trees do the same job in O of log of n. So how do they do it? They have a very efficient data structure. They make use of arrays. So they make use of the concept of bits. Here, let's see how it works. Suppose we have an array of size 8. So how they store the values? They store the values based on the last set bit of the index. Suppose our index is 1. It will store 1 itself. Suppose our index is 2. So last set bit is 2. So it will store itself and one another. So total 2. So it is 1, total 1. It is 4. Total 1, 2, 3, 4. Likewise 1, 1, 2, 1, and this is 8. So we got to know that every index stores something. So we can make use of it to find the prefix sum from starting to that index. And if we efficiently find that, we can find range queries easily. How? Suppose we want to have range query from A to B. What we can do is that we first find 1 to A minus 1 and 1 to B and get the difference of it. It will give us A minus B. So here, what do we have? First of all, we need queuing. How can we find the value of 1 to say 6? So let's see above here. We need to find 1 to 6. So first we go to 6. We see what is the last set bit. Here the last set bit is 2. So it stores 2 values. So we will just add it. So sum is initially 0. We will add. The number is, let's say it's number. So number is initially 0. Number or answer. Answer is initially 0. First we add the last set bit of this. Not the last set bit, the 6. The value at 6, we will add it. So whatever it is, now what we will do, we will just remove the last set bit. Remove it from here. And now what we are left with is 0, 1, 0, 0. So now what we do, we again find the value of this index. It is 4. So we are here. So we'll find the value of 4. It will contain the sum from this to this, from 4 to 1, and 6 will contain from 6 to 5. So like this we get the sum of 1 to 6 by having 1 to 5, 1 to 4 and 5 to 6. So this is how we will find out the value. This is how we query of sum from 1 to n, and likewise for we will reduce it for any range. So how can we find the last set bit? We can make use of this 2's complement. We will do this. Suppose our index is I, so at ith index we will do I and minus I. So it will give out the last set bit which is there. So what we will do with this, we will just add the last set bit, this thing. So first of all we have the index I, so answer is added with ARR of I. Then we will do I equals I and minus I. So the value of I, I minus equals 2, because every time we were removing the last set bit, this gives us last set bit and we are removing this from the initial index. So every time we will find out the next index, we have to add here. So finally it will give out the answer. So now the question is how to update. Update is also easy. So what we will do, here we have put a minus here. Suppose we have to update the value of, let's say 3 we have to update. So what we will do here, we will just add the value. Suppose we have a delta of 4 at 3, so we will add all the values which will come further by adding the last set bit to the number. Let's see how. So this is the number, our index 3. Any number would be there, so we will do delta is plus 4. So suppose at third we have 3, delta is plus 4, so 3 becomes 7. 3 plus 4, 7. Okay, so next index what do we need to update is 0 1 1, and we will add the last set bit. So the next index we will update is 100, the fourth one. So it would be, say it would be like it is 4, so 4 plus 4, 8. So the next index we will update is plus 1, the last set bit is 4 plus 1, 100, it is 8. So at 8 it is 8 plus 4, 12. So likewise we will go until we reach the end of the array. So the finding of last set bit is by I and minus I, and of I and minus I. This is our LSB, and this thing, the adding part, we will add I plus equals to, every time we will update the index, we will do how, we will add the last set bit to the original index, and we will just update every index of the array which comes, the index which is less than the last index of the array, obviously. So the I should be less than n, where n is the last index of our array, less than equals to, if n is the last index of our array. So here it's quite important. Then we just initiate a one index based Fenwick tree. So if we start from 0, so it becomes quite easy. So if we want 8, 3 4 5 6 7 and 8. So the this value goes to till 8 and the length is 9. So we will just do that key that I is less than equals to 8. So if I is less than equals to 8, it's good to go. But if it is greater, then we have to stop that. We have to stop updating because index overshoots. So what do we have till now? If we want to query sum from index int a to int b, what do we do? First of all, we will query, let's say we will query, we can do from a to b. If we can do from 1 to a, let's query from for int b from 1 to b. So how would we do that? We will do that by initializing answer to 0. Then we'll give a while loop while our index is greater than equals to 0. Our index is greater than 0. While our index is greater than 0, answer plus equals to array of I and I equals to I and minus I. And how would this is plus and minus. Since the last bit is last set bit we are removing every time while querying. So because while querying we go down, like if we have 6, first 2, then 4, like we have done, like it is 6, so last set bit is 2, then it is 4, and every time we remove them. So first 2 and then 4. So for the updation part, if we need to update delta at index I, let's say index I, we need to update. So for the updation, while I is less than equals to n is the last index, the length of the array is n minus 1, n plus 1, n are the number of values which are there. So while I is less than equals to n, we will do this thing, arr of I plus equals to delta, whatever it is, and we will update the index by I plus equals to I and minus I. This is the LSB, and we add it so that it goes for the next value to update, and we will return the required. If we want true, we just return void. It's just a update thing. We will return answer here in the query part. So that's how we will do. Hope you guys might have understood it. It's quite efficient way of finding the range sum queries. Thank you.